So in this exam style question, we're told that the graph below shows how the charge stored by a capacitor varies with time when it is discharged through a fixed resistor. So we're not using a variable resistor here. With a variable resistor, as we've seen, you can control the current in your circuit so that it's constant. When you have only a fixed resistor, you can't do that, and therefore your current is going to decrease over time as you discharge your capacitor. And so we have this graph here. We see we've got our charge in microcoulombs here. We start at 0.25 coulombs, and we see our time in milliseconds here. So the first thing I'd like us to do is explain how the initial current in the circuit could be determined from a graph of charge against time. So that requires us kind of really thinking about what current and charge kind of represent, or what they have to do with each other. We know that current is the rate of flow of charge, and so current is the gradient of a charge time graph. So we could find the initial current in our circuit just by looking at the initial slope of our graph here. So that leads us to our answer. We see that current is the rate of flow of charge, and so is the gradient of a charge time graph. To find the initial current, we could measure the initial slope of the graph above. In practice, what would that mean? Well, it would mean we would draw a straight line here. I won't do this in detail, but we just draw a straight line going down like this. That's a slightly better drawing of it. So we'd get a line like this, making it match up with the initial slope of our graph, and then from this we could simply find the gradient by noticing the distance along here, and this is also here. This is just a straight line graph, and so we could find the gradient like that, and from that we could find the initial current. That's not what we're doing here, so I'll delete this now so we don't get confused. Equally, remember that the charge is just the area under a current time graph. So this was a charge against time. If this were a current against time graph, we could find the initial charge on our capacitor by adding up the area under all of this graph, and then that would give us the initial charge if this were a current against time graph. So you can often be asked questions on relating the two of them, so it's good to know exactly what the relation is. The next part of our question asks us to determine the time constant in milliseconds of the discharge circuit. So remember, if you write out the equation for charge, remember that Q equals Q naught e to the minus T over RC, and remember that this RC is the time constant. So there's kind of two ways we can proceed here. Now, there's one which we didn't explicitly cover in the actual lessons we did, but we can practice that now, and we will. And the other option is the more laborious, just simple graphical approach. So we'll do the graphical approach first. That's where we realise, and this is probably the simplest way to say it, is that the time constant, we remember, tells us the time taken to fall to 37% of our original charge. A slightly better way of putting that is that the charge has decreased to 37% of its original value when t equals RC.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.